how do chemists know the exact 3D shape of a molecule they can't even see? It's not magic, I promise. It all comes down to one super simple idea, and that's what this explainer is all about. We're going to unpack VSEPR theory, which is your key to basically seeing the molecular world.
Right? I mean, you see H2O on a page. You know it's water. But how do we know it's bent? Why isn't it just a straight line? Or think about methane, CH4. How do we know it makes this perfect little pyramid shape? Well, the answer is a really powerful predictive model.
And that model is VSEPR theory. Yeah, VSEPR. It stands for valence shell electron pair repulsion. It's a total mouthful, I know, but the name literally tells you everything you need to know. It's all about one thing: how the electrons in an atom's outer shell, its valence shell, are constantly pushing each other away.
And here's the crazy part. The entire theory, all of it, boils down to this one single idea. This is the golden rule, okay? Electrons are negative. So what do? They repel each other. They push away from each other. So to get to the most stable shape, they're just going to get as far apart from each other as they possibly can. That's it. Seriously, that one concept is going to define every single shape we look at.
Okay, so here's our game plan. First, we'll nail down that core idea. Then we'll go through the simple rules you need to know. And after that, we'll walk through the actual shapes for 2, 3, and 4 electron domains. By the end of this, you'll be able to do this in your sleep.
All right, let's dive in. Section 1, the core idea. One concept to rule them all.
And this visual just says it all, right? Look, if you've got 2 groups of electrons, what's the farthest they can get from each other? 180 degrees apart, a straight line. Simple. Now, what about 3? Well, they'll spread out into a flat triangle. That's what we call trigonal planar. But with 4, see, they can't stay flat anymore. To get even further apart, they have to pop into 3D and form a tetrahedron. It's all just geometry, all driven by that simple repulsion.
Okay, hang on. Before we go any further, we have got to nail down 2 super important terms. They sound similar, but they are not the same. First, you've got electron domain geometry. That's the arrangement of everything around that central atom. We're talking all the bonds and any lone pairs. But then you have molecular geometry, and that's the shape of just the atoms. It's what you'd actually see if you could look at the molecule. The lone pairs, they're still there, totally pushing things around and influencing the shape, but they're kind of invisible when you go to name the final structure. Getting this difference is absolutely crucial. All right, on to section 2, the simple rules. This is your how-to guide.
Look, there are really only 2 rules you need to keep in your head. First, it doesn't matter if the electrons are in a bond or if they're a lone pair just hanging out, they all repel each other. And second, and this one is a biggie, so listen up, a double bond or a triple bond, it only counts as one electron domain. Just think of it like one big super bond, one group of electrons all pointing in the same direction.
So how do you do it? It's a simple 3-step recipe and it works every single time. Step 1, you gotta draw the Lewis structure. You need to see where all those valence electrons are. Step 2, you count up the total number of electron domains right around that central atom. And remember, that means all the bonds and all the lone pairs. And finally, step 3, you take that number, figure out the base electron domain geometry, and from there, you figure out the final molecular geometry by looking at where the atoms ended up. Oh, and a quick heads up on how we draw these 3D shapes on a flat screen. You're gonna see these wedge and dash things. The solid wedge, that bond is popping out towards you. The dashed one, that's going back, away from you. And a normal solid line is just flat on the page. Simple as that. Okay, let's actually do this. Section 3, 2 electron domains. We're starting with the easiest one. So if your central atom only has 2 electron domains and no lone pairs, this is a no-brainer. To get as far apart as possible, they're going to go to opposite sides, right? That's a 180-degree angle. So the electron domain geometry and the molecular geometry, they're exactly the same, linear. Think of something like carbon dioxide, CO2. It's a perfect straight line. All right, let's level up. Section 4, 3 electron domains. Now this is where it starts to get really interesting, because now lone pairs are going to come into play and start messing with the final shape. Okay, so here's the rule. If you count 3 electron domains around a central atom, the base shape, the electron domain geometry, is always going to be trigonal planar. No exceptions. The 3 groups just spread out to form a perfect flat triangle with 120 degrees between each of them. But now we have to think about the molecular geometry. So if all 3 of those domains are actual bonds, then the final shape is also trigonal planar. Easy.
But what if one of those domains is a lone pair? Well, that lone pair is still there, right? It's still pushing the other two bonds away from it. But remember, it's invisible. So what's the shape you actually see from the remaining atoms? It's bent. See that? That one little lone pair totally changes the name of the shape.
And that brings us to our last section for today, Section 5, 4 electron domains. This is where we get those classic tetrahedral shapes you see all the time.
And you can probably guess the pattern by now. When you've got 4 electron domains, they push each other into that 3D shape, the tetrahedron, because that's the only way to get maximum distance. So the base electron domain geometry for any molecule with 4 domains is always tetrahedral. Lock that in. Okay, let's break this down using the table. Case 1. 4 bonding domains, 0 lone pairs. Classic methane, CH4. The molecular geometry is, you guessed it, tetrahedral, same as the base shape. Now let's switch things up. Let's take away one bond and put in a lone pair. This is ammonia, NH3. That invisible lone pair is sitting on top, pushing the 3 hydrogens down and away, creating this little pyramid shape, so we call it trigonal pyramidal. And here's a really cool detail. That lone pair actually repels even more strongly than a bonding pair does. Think about it. It's bigger and fluffier because it's only being held by one atom. So what happens if we swap out a second bond for another lone pair, like in water, H2O? Well, now you have 2 of those super repulsive lone pairs, pushing the 2 little hydrogens even closer together. And what shape do you get? That classic bent shape we talked about at the very beginning. So, you see, the whole thing boils down to this one simple process. You count the domains to get the base shape, linear, trigonal planar, or tetrahedral. Then you just look to see how many of those are lone pairs, and that tells you the final molecular shape. It's a beautiful, predictable system. So let's wrap this up with a question for you. We've seen just how powerful this one little idea of electron repulsion is for predicting shapes, right? So what do you think happens when you go even further? What about molecules with 5 or even 6 electron domains? Or what about that little detail we just mentioned, that a lone pair repels more strongly than a bond? How does that tweak the exact angles? That's where things get even more interesting. But every single bit of it, builds on the exact foundation we just laid out.